Number 7. The Boltzmann brain. In the late 19th century, Austrian physicist Ludwig Boltzmann revolutionized our understanding of the universe with his work on thermodynamics and entropy. He established that the universe is constantly moving from a state of order to a state of complete and utter disorder. A dropped coffee mug shatters. It never spontaneously reassembles itself. Heat dissipates. It never concentrates back into a single point. This is the arrow of time. But Boltzmann's mathematics allowed for a terrifying loophole. Because the universe is governed by statistical mechanics and random quantum fluctuations, there is an infinitesimally small, yet mathematically non-zero chance that particles could randomly arrange themselves into a highly ordered state. Given an infinite amount of time, a universe sitting in total thermal equilibrium, a cold, dead, empty void, will eventually experience random quantum fluctuations. Particles will bump into each other. Over trillions upon trillions of eons, these random collisions will occasionally form complex structures. They might form a single molecule of water. Wait long enough, and they might form a rock. Wait even longer, and they will form a fully functioning, conscious human brain, complete with a network of neurons, false memories, and a sudden, fleeting perception of existence. This is the Boltzmann brain. What makes this paradox so profoundly disturbing is the mathematics of probability. In an infinite universe, the amount of time it takes for a complex, 13.8 billion-year-old cosmos filled with hundreds of billions of galaxies, stars, planets, and billions of conscious beings to evolve is staggeringly massive. The probability of a universe like ours existing exactly as it does is unimaginably low. However, the probability of a single, isolated brain spontaneously popping into existence from the quantum void, existing for just a fraction of a second, and hallucinating the exact experience you are having right now, is actually mathematically much higher. According to the pure laws of probability, there should be vastly more Boltzmann brains floating in the endless expanse of the cosmos than there are evolved human brains inside a structured universe. And this leads to a conclusion that keeps theoretical physicists awake at night. You cannot scientifically prove that you are not a Boltzmann brain. Your entire life, your childhood memories, the faces of your loved ones, the device you are reading this on, and the very concept of the universe itself might be a momentary cosmic hallucination. You might have simply popped into existence 1 microsecond ago in the middle of a dead, empty void, equipped with the false memory of a complete life. And in the very next microsecond, your atoms will disperse back into the thermal noise, erasing you forever. Everything you know and love is just a temporary glitch in the infinite dark. Number 6. The cosmological constant problem. In the early 20th century, physics was divided into 2 magnificent, flawlessly precise frameworks. General relativity, which describes the macro-universe of gravity, stars, and galaxies, and quantum mechanics, which governs the microscopic realm of atoms, quarks, and fundamental forces. For decades, scientists have tried to unite them. And every time they try, they hit a mathematical wall so catastrophic it is often referred to as the worst prediction in the history of science. This is the cosmological constant problem. The paradox arises when we look at empty space. According to quantum field theory, a vacuum is never truly empty. If you take a region of space, remove all the gas, all the dust, all the light, and absolutely every particle of matter, the space left behind is still boiling with energy. Virtual particles are constantly popping into and out of existence in a frantic quantum dance. This background energy of the universe is known as vacuum energy. When theoretical physicists use the flawless mathematics of quantum mechanics to calculate exactly how much energy should exist in this vacuum, they arrive at a massive number. The energy density of empty space should be completely overwhelming. But when astronomers actually look out into the universe and measure the cosmological constant, the mysterious dark energy that is actively pushing the universe apart and causing it to expand, they find a number that is drastically, almost comically, smaller. How much smaller? 120 orders of magnitude. That is a 1 followed by 120 zeros. To put that into perspective, there are only about 10 to the 80th power atoms in the entire observable universe. The discrepancy between what quantum mechanics predicts and what we actually observe is so vast that it breaks our understanding of reality. If the quantum calculations were correct, the vacuum energy of the universe would be so intense that the gravitational repulsion would have ripped the universe apart fractions of a second after the Big Bang. Stars could never have formed. Galaxies would have been shredded before they were born. Atoms themselves would be impossible. The universe would be a sterile, hyper-expanding emptiness. But we are here. The universe exists. This paradox forces us to confront a sobering reality. Our most fundamental models of existence, the very rules we use to build computers, launch satellites, and understand the stars, are broken at their absolute core. There is a hidden mechanism governing the fabric of space and time that completely defies human comprehension. We are floating in a cosmos that is balanced on a mathematical impossibility, and we have absolutely no idea why the universe hasn't torn itself to pieces. Number 5. The flatness problem. When cosmologists talk about the shape of the universe, they aren't talking about it looking like a sphere or a cube. They are talking about its fundamental geometry, specifically how parallel lines behave over massive cosmic distances. According to Einstein's theory of general relativity, the mass and energy of the universe warp and curve the fabric of spacetime. Depending on the exact density of matter and energy, the universe can take one of three shapes. It can be closed, like a sphere, where parallel lines eventually converge. It can be open, like a saddle, where parallel lines diverge. Or it can be perfectly flat, where parallel lines stay parallel forever. By measuring the cosmic microwave background radiation, the afterglow of the Big Bang, astronomers have determined that our universe is flat. Not just somewhat flat, but phenomenally, precisely flat, with a margin of error of less than 0.4%. And this is where the paradox begins. For the universe to be this perfectly flat today, 13.8 billion years after it was born, the initial conditions of the Big Bang had to be fine-tuned to an absurd, incomprehensible degree. The density of the universe is represented by a parameter called omega. For the universe to be flat, omega must exactly equal 1. If omega is slightly more than 1, the gravity of the universe overpowers its expansion, and everything eventually collapses back in on itself in a violent big crunch. If omega is slightly less than 1, the expansion outpaces gravity so rapidly that matter is scattered to the wind, stars never ignite, and the universe instantly becomes a frozen, dead expanse. Because the universe expands, any slight deviation from perfect flatness in the beginning would have been amplified trillions of times over. For omega to be near 1 today, the density of the universe just 1 nanosecond after the Big Bang had to be perfectly fine-tuned to within 1 part in 10 to the 62nd power. That is a precision comparable to throwing a single dart from the surface of the Earth and hitting a target the size of a single atom on the furthest edge of the observable universe. The flatness problem is an existential nightmare, because it implies that our existence is either the result of an impossibly specific cosmic accident, or our entire universe is just a localized, temporary bubble. It suggests that reality is walking a razor-thin tightrope over an abyss of non-existence. If the universe had been heavier by a fraction of an ounce, we would have been crushed. If it had been lighter, we would be frozen in the dark. We exist on the absolute knife edge of cosmic probability, and science cannot fully explain who or what balanced the scales. Number 4. The horizon problem. When you look up at the night sky, you are looking back in time. The light from a star, 10 light-years away, takes 10 years to reach your eyes. This means there is a strict speed limit to how fast information and energy can travel through the universe, the speed of light. Because the universe is 13.8 billion years old, there is a limit to how far we can see, creating what we call the observable universe. In the 1960s, astronomers discovered the cosmic microwave background, CMB, radiation. This is the primordial heat left over from the Big Bang, a faint wash of microwave radiation permeating every single inch of the cosmos. When scientists mapped this radiation, they found something deeply unsettling. The temperature of the CMB is almost exactly the same everywhere you look. It sits at a freezing 2.7 Kelvin, with variations of only a few 10,000ths of a degree. Here is why that is impossible. Imagine taking a cup of boiling water and a cup of freezing water and mixing them together. Eventually, they will balance out to room temperature. This process of thermal equilibrium requires time and contact. Heat must have the physical opportunity to travel from the hot region to the cold region. When we look at the cosmic microwave background, we are looking at opposite edges of the observable universe, regions of space that are currently separated by 93 billion light-years. These regions are so vastly distant that light itself hasn't had enough time since the dawn of the universe to travel between them. They have never touched. They have never exchanged information. They are entirely separate causal horizons. So how do they know to be the exact same temperature? This is the horizon problem. It is a fundamental paradox that violates the core principle of causality. If opposite sides of the universe have never been in contact, they should not share the exact same thermal signature. It is like opening two sealed vaults on opposite sides of the planet that have been locked since the dawn of time, and finding that the air inside them is circulating in the exact same pattern. To solve this, cosmologists propose the theory of cosmic inflation, a brief, violent period, fractions of a second after the Big Bang, where the universe expanded faster than the speed of light, stretching a once-connected, microscopic patch of space to cosmic proportions. But inflation remains a theoretical band-aid. What remains is that disparate regions of our universe mirror each other across impassable oceans of darkness. It forces us to ask whether the fundamental speed limit of reality is an illusion, or if the fabric of space is communicating through higher dimensions that human beings will never be able to perceive. Number 3. The black hole information paradox. Black holes are the ultimate monsters of the cosmos. They are regions of space where gravity is so intense that the fabric of reality itself collapses into a point of infinite density called a singularity. The boundary surrounding a black hole is known as the event horizon. Once anything crosses the event horizon, a star, a planet, or a beam of light, it is gone forever. Nothing can escape. But in 1974, theoretical physicist Stephen Hawking discovered something that shook the foundation of modern physics. He realized that black holes aren't completely black. Due to quantum fluctuations at the edge of the event horizon, black holes leak a tiny amount of thermal energy. Over unimaginable trillions of years, this Hawking radiation causes the black hole to slowly lose mass. Eventually, the black hole evaporates completely, leaving absolutely nothing behind. This discovery created the most profound crisis in modern physics, the information paradox. In quantum mechanics, there is a fundamental, unbreakable law. Information can never be destroyed. The physical universe operates like a cosmic ledger. If you burn a book, the information inside that book isn't technically lost. It has been converted into ash, smoke, and heat. If you possessed a theoretical supercomputer powerful enough to track the exact trajectory of every single molecule of smoke and every photon of heat, you could perfectly reconstruct the book. The universe always remembers. The past is always preserved in the present arrangement of particles. But when a book falls into a black hole, it crosses the event horizon and is crushed into the singularity. According to general relativity, it is locked away. Then, Hawking radiation causes the black hole to evaporate. But Hawking radiation is totally random. It contains no information about the things that fell into the black hole. When the black hole finally vanishes, where does the information go? It disappears. Forever. This is a direct, violent collision between the two pillars of reality. General relativity says the information must be destroyed. Quantum mechanics says the destruction of information is physically impossible. If information is truly lost, it means the bedrock of quantum physics is wrong. It means the universe is inherently unpredictable. It means that the past can literally be erased from existence. If the cosmos can delete information without a trace, then causality itself is an illusion. It implies that history has no permanent anchor in reality. The things that happened yesterday, 1,000 years ago, or 1 billion years ago, could be wiped from the cosmic ledger as if they never occurred at all. We are left staring into a void that not only consumes matter, but consumes the very concept of reality itself. Number 2. The Fermi paradox. In 1950, while walking to lunch at the Los Alamos National Laboratory, Nobel Prize-winning physicist Enrico Fermi looked up at his colleagues and asked a simple, terrifying question. Where is everybody? Our universe is staggeringly, unimaginably ancient. It is 13.8 billion years old. Our Milky Way galaxy alone contains an estimated 100 to 400 billion stars. Orbiting those stars are hundreds of billions of planets. According to the most conservative astronomical estimates, there are at least 40 billion Earth-sized rocky planets existing within the habitable zones of their host stars just in our galaxy. Our own solar system is a relative newcomer, forming a mere 4.5 billion years ago. There are star systems out there that are billions of years older than ours. Given the sheer volume of time and the vast number of habitable worlds, the evolution of life should not just be possible, it should be a statistical certainty. Even if the emergence of intelligent life is incredibly rare, the sheer numbers dictate that the Milky Way should be teeming with advanced civilizations. If an alien species had an evolutionary head start of just 1 million years, a blink of an eye in cosmic time, they would have had ample time to colonize the entire galaxy, build Dyson spheres that enclose entire stars, and leave behind detectable technological signatures that scream their presence into the void. Yet, when we turn our massive radio telescopes to the sky, when we scan the billions of star systems looking for lasers, radio waves, or the infrared heat of megastructures, we hear absolutely nothing. The sky is completely, profoundly silent. This is the Fermi paradox. The math says they should be everywhere. The observation says we are entirely alone. To resolve this paradox, scientists propose the concept of the Great Filter. The theory states that, in the evolutionary timeline of any intelligent species, there is a universally fatal barrier, a hurdle so difficult to overcome that virtually no civilization survives it. It acts as a cosmic exterminator, wiping out species before they can become spacefaring and colonize the galaxy. The darkest implication of the Great Filter is a matter of timing. Are we past the filter, or is it ahead of us? If the filter is behind us, perhaps the jump from single-celled organisms to complex life is nearly impossible, then we might truly be the first and only intelligent species in the galaxy. We are a solitary fluke of nature. But if the filter is ahead of us, the implications are apocalyptic. It means that across billions of years, thousands of advanced alien civilizations have risen, built cities, looked up at the stars, and then encountered a barrier that annihilated them. It could be nuclear self-destruction, engineered pandemics, runaway artificial intelligence, or catastrophic climate collapse. If the Great Filter is in our future, then our silence in the cosmos is not a sign of our uniqueness. It is a graveyard. It means that the fatal test that wiped out everyone else is waiting for us right around the corner, and our ultimate extinction is a cosmic inevitability. Number 1. Olber's paradox. Sometimes, the most haunting mysteries in the universe hide behind the most innocent questions. In the 1820s, German astronomer Heinrich Wilhelm Olbers formulated a paradox based on an observation so simple that a child could make it. Why is the night sky dark? For centuries, astronomers believed that the universe was infinite, timeless, and static. They believed it stretched on forever in every direction and had existed for an eternity. But Olbers realized a fatal flaw in this logic. Imagine standing in the middle of an infinitely dense, perfectly uniform forest. No matter which direction you look, your line of sight will eventually hit the trunk of a tree. You would not be able to see any gaps. Your entire field of vision would be a solid wall of wood. The same logic applies to an infinite static universe filled with stars. If the universe goes on forever, and has existed forever, then every single point in the night sky should eventually intersect with the surface of a star. Even if a star is millions of light years away, in an eternal universe, its light would have had plenty of time to reach us. Therefore, the night sky should not be dark. Every square inch of the heavens above us should be a solid, blinding wall of starlight. The night sky should glow with the intense, scorching heat of the surface of the sun, but it doesn't. We are surrounded by an abyss of black space dotted with tiny pinpricks of light. The resolution to Olber's paradox overturned our understanding of our place in reality. The night sky is dark because the universe is not infinite and it is not eternal. The darkness is physical proof that the universe had a violent beginning. We can only see the light from stars that have had time to reach us since the Big Bang 13.8 billion years ago. But the paradox holds an even more unsettling implication. The universe is expanding, and that expansion is accelerating. The space between galaxies is stretching out so fast that the light from distant stars is being stretched into long, invisible infrared and radio waves, a phenomenon known as cosmological redshift. The stars are quite literally running away from us faster than their light can reach us. The darkness of the night sky is not just an absence of light. It is visual proof of our cosmic mortality. It is the shadow of our immense isolation. When you look up into the blackness between the stars, you are staring into the rapidly expanding void that is actively isolating us from the rest of the cosmos. Trillions of years from now, the expansion will be so severe that no stars outside our immediate galactic neighborhood will be visible at all. Future civilizations, if they exist, will look up into a completely featureless, terrifyingly empty black sky, unaware that a wider universe ever existed. The darkness we see every night is the slowly closing curtain on